Hi everyone. We're now looking at the first handout from section 5.1 that involves the probability for discrete random variables and calculating the mean and the standard deviation of these. Now the first thing that we talked about, if you remember from the reading, the discrete probability distributions is a listing of each of the possible outcomes in such a way that, for example, x could be anything from 0 to 5, and then we have the probability for each one. So if x was 0, the probability would be equal to 0.048. Now there were two rules that we associated with this. The first one was that each of these numbers here has to be between 0 and 1, and they are, so that's okay. They are all between 0 and 1. But the second rule is that when you add them all up together, they're supposed to sum to 1. Now if you add all these numbers up together, you get 1.039, which is not possible for a probability. Okay, moving to the second problem, we have similarly, we have x could be anything from 0 to 10, and the probabilities that are listed next to each possible outcome are all between 0 and 1, but if you add them all up, they add to 1.009. So neither one of these first two are probability distributions. These ones fail. So this one is not a probability distribution. And that goes for both of the first two. That one and that one as well. Because they don't sum up to 1 like they're supposed to. Now as we get to the third probability distribution, this one actually does work. All of the numbers from x equals 0, 1, 2, 3, 4, or 5 through then looking at all the probabilities associated with those numbers are all between 0 and 1, and when you add them up you do get 1.000. So this one is a probability distribution. Yay, we found one. Well, lucky for us, because now we get to use that in problem number 2, right down here. Okay, so here we go. We've got the same exact probability distribution right there. What we're supposed to do is use that information to find, make a probability histogram, then find some probabilities, etc. Okay, so let me first get rid of this big thing I made there. Okay. So the first thing we need to do if we're going to make a probability histogram is we need to have an x and y axis. And so I will make that right now. Okay, so we have an x and a y axis, and now we need to have probabilities for x equals 0, or 1, or 2, or 3, or 4, or 5. And the probabilities on the vertical axis get about as high as about 0.34 at most. So I'm going to go up by 0.1, 0.2, 0.3, and 0.4. All right. So if I add the bars, x is 0 goes up to 0.078, so a little bit less than 0.1. So that's about right there, maybe. And then 1 goes up to 0.259, so that's about 0.26. It's about right there. And 2 goes up to 0.346, so that goes all the way up to about halfway between the 0.3 and the 0.4. Then 3 goes to 0.230, so a little less than the other one we had. And then 4 goes up to 0.077 again, so that's almost exactly the same as the first bar. And then 5 is down to 0.010, so that's that's just barely down there. And that's a probability histogram. And when you have a probability histogram, we can talk about its shape. We can see, is it going to be bell-shaped? This one looks like it's maybe slightly skewed to the right. Okay, continuing, that's part A. We have now made the probability histogram for x. Now part B says find the probability that x is equal to 2. Get rid of these arrows. All right, so the probability that x equals 2 we can find right here. probability that x equals 2 is 0.346. That's just equal to 0.346. Now, if we want to do the probability that x is greater than or equal to 2, well, that means we need 2. We also need 3 and 4 and 5, because those are the numbers that are all greater than or equal to 2. So what that means is we need to total these guys up. Remember, the word or really means and. I mean, it means to add in probability. When you say or, you mean you need to add these things up. And when you add up 0.346 plus 0.230 plus that plus 0.077 plus 0.01, what you get is 0.663. 0.663. Now, if you want the probability that x is less than 4, well, that's a little different looking. That would be 0, 1, 2, and 3. So those guys, the green ones, added up. If you add them up, you could also just say, well, how about we do it this way? We use the complements. It's 1 minus 0.077 and minus 0.010. And 1 minus 0.077 and then a minus 0.010 is equal to 0.913. Or you could have just added the green ones up all together and you would still get 0.913. All right, now we have to find the mean number of lights. The mean number of lights means the average. So let's get rid of this. And we will create, to find the mean, I will use green. We need x times p of x, and then we have to sum that up. Okay? So we'll have 0 times 0.078, well, that's just 0.000. 1 times 0.259 is 0.259. 2 times 0.346 is going to be 0.692. 3 times 0.230 is 0.690. 4 times 0.077 is 0.308. And 5 times 0.010 is 0.050. And when you add up all those guys together, what you get is 1.999, or basically approximately equal to 2. What that means is you expect to see 2 green lights on the way to work. Okay, the last question is, would it be unusual for all 5 lights to be green? So you've got to remember what unusual means. Unusual means less than a 5% chance. Okay, so what's the probability that we have all 5 lights green? That's right here, 0.010. So the probability that x is equal to 5 is equal to 0.01, which is 1%. So that tells us that, yes, that would be unusual. As anyone who's driven can tell you, it's very unusual if you happen to hit that many green lights in a row. Okay, problem number 3 is very similar. The same kind of problems that we just did. And problem number 4 is a probability distribution that gives the number of 3-point shots made per game by Steph Curry during the 2016-2017 season. The difference is I'm going to use StatCrunch to compute this. Okay, so the first thing I do is I need to get this data into StatCrunch because, of course, it's going to be easier. Now, we could find the mean the same way we did before, but I would rather just do this, just copy this table and paste it over into StatCrunch, which is what I will do right now. I think I'm not going to show you every step. Let's just go through and see what we get. Okay, so I have pasted the 3-point shots made per game by Steph Curry into StatCrunch. Now we can see the probabilities. So the way that this data works is if you went to see Steph Curry play in a game, the chance that he would make 6 3-pointers exactly in that game would be 0.1, just about a 10.4% chance he's going to make exactly 6 3-pointers. The first question I think we're asked is, let's see, what is the probability he makes 5 3-point shots? Okay, well, the probability he makes 5 3-point shots, we can figure that out right very easily. It's 0.167, a 16.7% chance. Part B asks, what is the probability he makes at least 5 3-point shots? Well, at least 5 3-point shots means we have to add up all of these values together, which won't take too long, but there is another way to do it, and that's what I'm going to show you right now. It's also going to help us find the average number of 3-point shots he makes per game, and it'll help us find the standard deviation. So let me just show you how that works. Back to StatCrunch. StatCrunch! All right, so I have a probability distribution here. Although it's not one that we don't know what it is, so I have to use stat, calculators, and then custom, because this is a custom one. It really only works for Steph Curry. I select the variable is 3-pointers, number of 3-point shots he's going to make. Notice that is discrete, right? He can't make 2.5 3-point shots. He's got to make 2 or 3 or 4 or 5. The weights is probability, and then I click compute. And this is the probability distribution. Okay, notice it gives you the mean, 4.96, so basically about 5. So on average, Steph Curry makes about 5 3-point shots per game. At least he did in the 2016-2017 season. About 5 a game, and the standard deviation is about 2.4, which means that you figure most of the time he's going to get between 5 and 7 and maybe 3. So 3 to 7, 3 to 8 is what he's going to get in any particular game. Now the problem asked us, what was the probability that he got, let's click back here for a second, at least 5 3-point shots. If you want at least 5 3-point shots, that means greater than or equal to 5. So I'm going to change this to greater than or equal to. We've already got a 5 there, and it's 0.542. 4 places, 0.5421. So there's about a 54% chance he's going to make at least 5 3-point shots in the game, which of course is very exciting. Now, we already have answered what's the standard deviation, and we found the average number of 3-point shots he makes per game. Looking down at part E, finally, would it be unusual to see a Warriors game in which Steph Curry made 10 or more 3-point shots? But we don't actually need StatCrunch to do that. We just need to add up 10 or more 3-point shots right here. 0.021 plus 0.01 and 0.01 adds up to 0.041, which is less than 5% chance. So yes, it would be unusual to see Steph Curry get more than 10 or more 3-point shots made in one game. Doesn't mean it couldn't happen, and it has happened, but it's not the norm. It's not what happens usually. So thanks, and please send me any emails if you have any questions. I'll try to get back to you as soon as I can. Thanks, goodbye, and be safe.